Hey team, this is going to be a walkthrough of the Level 3 Calculus 2024 integration paper. As ever, if you're doing this paper from scratch, have a go at each question, pause me before I tell you how to do it, give it a go yourselves, and if you get stuck and you want to check how you're getting on, then press play and listening. Make sure you've got your resource sheet, calculator, pen, pencil, stuff like that to hand, and we'll jump straight in. Question 1. Now, for question 1, we are told to find the integral of 6 sec of 2x multiplied by the tangent 2x with respect to dx. Now, with these sorts of questions, if you ever get a really complicated integral with a mixture of different trigonometric functions, always check the resource sheet, because chances are there will be a standard integration given to you on the resource sheet somewhere in there. And for us, for this question, the relevant part is in the calculus differentiation table. So we have that if y is equal to f of x is sec x, then the differentiated form will be sec of the angle multiplied by tan of the same angle. We're integrating this, and so we're going to end up with the original function, which was just sec x. Now, because we have a 2 inside our brackets on the angle, it means that we have to divide by the differentiated contents of the brackets here. So the integral of this becomes 6 sec x, 6 sec of 2x divided by 2 plus c, which we can then simplify down to 3 sec of 2x plus c. Now, the reason that you still have to divide by the 2 is because really this is actually a form of, well, we're making use of the chain rule to do this integration. If I rewrite sec of 2x and tan x in terms of sine and cos, what we're actually integrating is 6 sine 2x, which is from the tan, and then sec is 1 over cos, tan is sine over cos, so cos squared of 2x, which again can be rewritten as the integral of 6 sine 2x cos minus 2x with respect to x. Okay, and you can see here that if we were to integrate this, that this sine term is the differentiated form of cosine to the power of minus 2. The coefficients figure themselves out, but this is actually a form of the chain rule. And so you do need to divide by the differentiated contents of your trigonometric terms here. Okay, to achieve that question, just for getting 3 sec 2x plus c. And my laptop's about to update, so I'm going to pause this immediately and restart it. Sorry, I'm back. Now for part B, we are told that the graph below shows the function y is equal to 40x multiplied by 5x squared minus 3 all cubed. And we are told to find the shaded area using calculus, showing the results of any integration needed to solve the problem. Okay, now when we have this sort of expression here, it is possible to expand it and integrate each of the individual x terms. That's quite time consuming. And so a little shortcut is, again, here, this is an example of another chain rule or inverse chain rule that we're going to apply to this. If you have a bracketed term with powers of x in there, and then one less power of x outside of the brackets, usually it's an indication that you can apply the inverse chain rule to this expression. And so that's what we're going to do. Now, in the graph, we are given our limits for our integration. So this will be a defined integration between 0.4 and 0. And so we'll jump straight into that. Now, as we're doing the inverse chain rule, we have to divide our entire resultant expression by the differentiated form of what's inside the brackets. Because we've got a 5x squared term in here, that thing we're going to divide by is 10x. So our 40x sorry, can you move it up? Our 40x remains outside the front. We have our 5x squared minus 3. This time we are raising the power of 3 up to 4. We're adding 1 because we are integrating it. We have to divide by this new power, which is 4. And as I just said, we need to divide by the differentiated contents of this bracket. So the minus 3 just disappears. 5x squared differentiates to 10x. And so we have to divide our resulting expression by that. Because this is the result of our integration, we're going to have 0 minus 0.4 in our square brackets. And then we just go through and we can cancel out 4 lots of 10x of 40x, which cancels with the 40x on the top. Leaving us with 5x squared minus 3 to the 4th power in the range 0 to 0.4. And now we substitute our two respective values for x in, and we find the value of our integral. Just being really careful with your brackets, making sure that everything that should be squared or to the quartic are, and anything that isn't is not. And then you type it into your calculator and you should get yourselves a numerical answer. So my first bracket, when this x becomes 0, this 5 times x squared term becomes 0. So we're left with just 3 to the quartic, or 81, minus, then we're going to type out this whole thing, 5 times minus 0.4 squared. And we'll wrap those all up in brackets, and then another set. Like so. And you should find that your second bracketed term comes to 23.4256. Now, I've used a hell of a lot of brackets just to make sure that my calculator squares when I want it to square and puts to the quarter or to the 4th power what I want it to do so. Okay, so we have 81 minus 23.4256 is equal to 81 minus answer 57.5744 u squared, or unit squared, however you would like to do that. Now, if you follow this all the way through to 57.5744 units squared, that is an achieved question. If you missed out these units at the end, you still get achieved. It's not required to do that. It looks like if you do not have sufficient evidence of your integration, or if you don't have the correct answer at the end, you get no credit. So accuracy is important. Now, on to part C. We are told that an object's velocity can be modelled by the equation v with respect to t is equal to 26.4 multiplied by the cubic root of t, where v is the velocity of the object in meters per second and t is the time in seconds since the start of timing. Initially, the object was 360 meters from a point P. Calculate the distance that this object has travelled from the point P when it has reached a velocity of 264 meters per second. Now, if we're given our function for velocity with respect to t, hopefully we recall that we have this sort of cascading series of distance and acceleration with respect to t as well. In order to go from velocity to distance, or displacement, sorry, hence the S, we have to integrate our velocity term. Obviously, this is an integration paper. Every question you are going to be integrating. So we'll jump straight into it. D with respect to t will be equal to the integral of 26.4 cube root of t. We have not got any limits in our integrand because this is just an undefined integration question. Now, this is not a particularly advantageous way to write out the expression. So I'm going to change this cube root to index form, which doesn't change anything about the expression other than it makes our integration a bit easier. And obviously, sorry, we are integrating with respect to t here. So now that I put my cube root, sorry, to the third power, or sorry, a power of a third. Remember, with any root, you just put 1 over the root that it is to, as your power. And then we can just add 1 to the power and divide by the new power with our resultant expression. So if we raise the power of t by 1, we end up adding 3/3 to it, which gives us a total power of 4/3. And then, sorry, my square bracket's not long enough. We're dividing by the new power of 4/3. Okay, and I'm forgetting that this isn't a defined integration question, so we have our constant of integration added out the side. Sorry, my mistake. And then you can go through and just simplify these decimal terms. So 26.4 divided by 4/3. Divided by 4 times by 3 gives us 19.8. T to the power of 4/3 plus our constant of integration, c. Now, we are told that initially the object was 360 meters from a point P. Therefore, we have that, the distance at t equals 0, distance of the distance function at t equals 0 is equal to 360. Therefore, 360 must be equal to 19.8 multiplied by 0 to the power of 4/3 plus c. 0 to the power of 4/3 is just 0. 19.8 times 0 is just 0. Therefore, 360 is equal to c on its own. And so our expression for distance d with respect to t is equal to 19.8 t to the power of 4/3 plus 360. Now, when we have this is our expression for distance. We are told to calculate the distance travelled from the point P when it's at a velocity of 264. So now we've got our expression for distance. We can find out at what time this velocity occurs by using our original expression for velocity. Vt is equal to 264, therefore equals to 26.4, times by t to the power of a third. Then you can see if we divide both sides by 26.4, we have 10 is equal to the cube root of t to the power of a third. Therefore, t is equal to 10 cubed, which is equal to 1,000. T equals 1,000 seconds at v equals 264 meters per second. Sorry, off the end of the page. So now we have our time that this velocity took place in. We can substitute this value of t back into our found expression function for distance, and we can have that d of 1,000 is equal to 19.8 multiplied by 1,000 to the power of 4/3 plus 360. You pop that in your calculator, 19.8 times 1,000 4 divided by 3 plus 360. We have 198,360 meters. Now, if you followed that through to this final answer, that was enough for merit. You had to have evidence of integration to get to your expression for distance or displacement. And then for the achieve mark alone, you needed to get to your actual expression for distance, So that was needed for achieve, finding the time that the velocity of 264 occurred at, and then subbing that into your formula for a distance gives you your final answer and merit. Now to question D, we are asked to consider the differential equation dy by dx is equal to 24 cosine of 3x multiplied by sine of x. Given that y is equal to 6 when x is equal to pi over 3, find the values of y when x is equal to pi divided by 2. Now, we are naturally going to be integrating this expression up here, this equation up here. And so we are going to be performing the integration of 24 cos 3x sine of x with respect to x. Now, this is not doable for us. And so, again, if you ever have these weird combinations of sine and cosine terms, always look at your resource sheet for one of the trig identities. Now, we've got a cosine and sine term with differing angles inside them multiplied together. And so we're trying to replace this product of two trigonometric terms with, hopefully, some terms added together. So this will be in the product section of your trig ID pages on the resource sheet. We have cosine. If you look down the list of the identities are given, I'm just going to write down the relevant one. We have that 2 cos of an angle A multiplied by the sine of the angle B is equal to sine A plus B minus sine of the angle that is the difference between our two original angles. Now, if we make this equivalency into our expression up here, we have this factor of 2 that isn't present here. So we are going to divide this 24 by 2. So our integral becomes 12 all multiplying sine of our angle A, which is 3x, plus our angle B, which is x. 3x plus x is 4x. And then we are subtracting sine, where the angle here is the difference of the two, 3x minus x, which is just 2x. With respect to x here. Now, what I'm going to do, I'm going to make this a bit easier to write and lay out for myself by moving the 12 out of the integrand, just because then I can faff around with the brackets a bit less. And it's also just a reminder to myself that it's not involved, it's just a spectator. Only the x terms are going to be integrated. Now we can integrate sine fairly easily, and so we can have 12 multiplied by cosine of 4x divided by 4, and because we're integrating sine, we're going back to negative cosine. Okay, now It's an important thing to remember. If you're differentiating sine, you get positive cos. Therefore, if you're integrating sine, you must get a negative cosine term here. Now, because here, our second term in the expression is a negative sign to begin with, when we integrate, if we were just to integrate sine, ignoring the negative term, we'd get a negative cosine minus a minus becomes a positive, so it will change to be a positive term here. If you're integrating minus sine and you are including the minus, you get back to positive cosine anyway. Either way you cut it, we have positive cos of 2x divided by 2 this time. Plus some constant of integration c. Because we have no limits in our integrand, we have to add our constant of integration. Going forwards, I'm just going to tidy up this expression, switch positions just so I have to write a bit less. I haven't got to write an extra plus sign, and I'm going to also simplify these numerical terms. So expanding the brackets, I have 12 cosine of 2x divided by 2, which is 6 cosine of 2x, minus 12 over 4, which is 3 cosine of 4x, plus c. So now that we have an expression for y, now that we've integrated dy by dx, we are back at y. We have this undefined value c. We are given some x and y coordinates in the question. We are given that y is equal to 6 when x is equal to pi divided by 3. And so we can use those two values, y and x, to find our constant of integration c. So when y is equal to 6, make that substitution straight away, 6 cosine of 2x, which is 2 pi over 3, minus 3 cosine of 4 pi over 3 plus c. Therefore, c is equal to 6 minus 6 cosine 2 pi over 3 plus 3 cos 4 pi over 3. And I'm going to skip me typing this into a calculator and just get to the answer. And you should find that your value of c is 7.5. Now remember, whenever you see x values given in terms of pi, naturally we should be working in radians. Now that we have our constant of integration, I'm just going to rewrite the full expression with it included, just because that sometimes can be the requirement for a merit mark. 2x minus 3 cosine 4x plus 7.5. Now the question wanted us to find the values of y when x is equal to pi over 2. So now we're going to go down and substitute when x is equal to pi over 2, y is equal to 6 cosine pi over 2 multiplied by 2 is pi, minus 3 cosine 4 pi divided by 2 is 2 pi, plus 7.5. Now if you remember your cosine graphs, it's good little practice for you here. You can do this in the calculator if you want, don't need to. From your cosine graph, we have that at 0, cosine is equal to 1, therefore at pi, cosine is equal to minus 1. So it's 6 lots of minus 1 minus 3 lots of at 2 pi, now it's plus 1 again. So we have 3 lots of 1 plus 7.5. Therefore, y is equal to minus 6 minus 3, which comes to minus 9 plus 7.5. is minus 1.5. Now, if you follow through to get your value of y here, that is merit as long as you have evidence of integration. If you integrated the expression correctly, resulting in your two cosine terms down here, then that's what you need to do for achieve. Therefore, it's expected that you are making use of this trig ID. You don't get any credit for doing that. Harsh or not harsh, you decide. Now, for question E, we are told that the graph below shows the curves y is equal to 3 sec squared x and y is equal to 2 tan squared x, which are both drawn on. We are told to find the area of the shaded region enclosed by the two curves x equals 1 and the y-axis. So we have both of our limits for our integrations. We are going to be doing defined integration. And the idea is, in order to work out this grey section, we are going to work out the total area beneath the 3 sec squared x curve, and then we're going to take away the area underneath our second curve here to get rid of this white space, just leaving us with this section between the two. So we are going to have that I'm going to write it up here just for clarity. A shaded is equal to the area under the sec squared curve minus the area under the tan squared curve. That's not very thoroughly written out, it's just as a vague idea. That's the logic we're using for this integration. Now, to find the area under the curves, I need to integrate both equations. So I'm going to be integrating between x equals 1 and x equals 0, because that's where the y-axis occurs. My 3 sec squared x minus 2 tan squared x, both with respect to x. Now, if you look on your resource sheet, you'll see that we have a standard integration for sec squared, which is arriving at just tangent on its own. We do not have a standard integration pattern for tan squared. However, if you go down to your trig IDs again, if you get these complicated trigonometric terms you're not sure how to deal with, have a look at your identities page and you should find one. The one that we're going to use here isn't useful immediately, but we have that tan squared from our resource sheets in terms of theta. Tan squared theta plus 1 is equal to sec squared theta. Therefore, tan squared theta will be equal to sec squared theta subtract 1. So I'm just going to substitute my two tan squareds here for tan squared theta is equal to sec squared theta minus 1. And obviously, because in this equation, in our integral, we're in terms of x, not theta, I am going to use x instead. So between 1 and 0, I'm going to be integrating 3 lots of sec squared x minus 2 lots of sec squared x minus 1 with respect to x. Now you can see this is advantageous for us in a few different ways. We've got rid of the horrible tan squared, but we also have a situation where these two like terms can be gathered up and making this integration far, far easier than it first looked. So we're going to integrate between 1 and 0. We have 3 sec squared. Once we've expanded out these brackets, this would be a 2 sec squared x, and I'm going to just simplify that straight away to 1 sec squared x minus 2 with respect to x. Okay, now the 2 is multiplying both of these terms, so make sure it is a minus 2, not a minus 1. Now, what we get to do is actually integrate. And as this is in your resource sheet as a standard differentiation from tan to sec squared, it's also a standard integration from sec squared to tangent. We can have our square brackets on because we have defined bounds for this integration, and it's tan of x minus 2x between 1 and 0. Therefore, when we substitute that in, we should get tan of 1 minus 2 lots of 1, all minus tan of 0 minus 0. You can do this in a calculator to prove it to yourself, or if you remember your tan curves, we have this, so tan of 0 will be 0, minus 0 is 0. This second bracket just collapses to 0. Therefore, you can just work out tan of 1 radian minus 2. Oh, sorry, no, it shouldn't be minus 2, it should be plus 2. And the reason why is up here, this is the trouble when you don't show all steps of your working, you start skipping stuff. We have minus 2 times minus 1. Minus 2 times minus 1 does not make negative 2, it makes positive 2. So just go back through, and I'll add my pluses in. Therefore, when I put through my answer, I have tan of 1, which is 1.5574, plus 2 is equal to 3.5574 units squared. Okay. Now that's a really important point to make. Being really careful with all these integrations and these negative symbols flying around. And obviously, yeah, if you do have a minus multiplied by minus, it always makes a positive product. So just be super, super careful with that. Now, if I hadn't done that, I would have given myself a negative area as an answer, which isn't possible. So that would be a big indicator to you that you've made a little mistake, as it was a big indicator to me that I had made a mistake. So yeah, for this final answer, 3.557, you would get E8, I believe. Sorry, marks came up. Correct solution with evidence of correct integrations. So I would have got E8 for that. If I had forgotten my negative, it sounds like I would have got E7 solution with a minor error. The one little negative sign escaped me. It would have taken me down to E7. If you did both integrations of both terms correctly, so going from sec squared to tan, or from 2 to 2x, then that was what you needed for merit. If you did any one integration correctly, that was enough for achieve. Now, looking at the mark scheme, they have done it slightly differently in that they have kept the sec squared minus 1 or the 2 sec squared minus 2 terms separate. They haven't involved them with this. I would imagine that's because you get achieved for just doing one integration correctly, and so they've integrated sec squared, then have used the trig ID to change tan squared. So yeah. The rounding isn't important, and they ask, or they don't even ask you for any units, so you do not need to worry about your units or u squared. For the full answer, it's E8 though, and that's question 1. Now on to question 2. We are told to find the integral of 3x to the power 4 plus 4 all squared with respect to x. Now because we have x to the power 4 inside the brackets, and we have not got an x cubed term outside the brackets, there's no inverse chain rule that we can apply. Because this is a quadratic, it's actually not too laborious to expand these brackets out. So that's what we are going to do, because then we just have 3 individual x terms that we can integrate normally. So 3x to the power 4 plus 4 squared using FOIL. Our firsts multiplied together is 3x to the power 4 multiplied by 3x to the power 4, which is 9x to the power of 8, adding our powers when we multiply them together. Then our outers are 3x to the power 4 times 4, which is 12x to the power 4. The inners will be the same. And then our lasts are 4 times 4, so plus 16. So I'm going to just rewrite that into my integrand, combining these two like terms. So we are integrating 9x to the power of 8 plus 24x to the power of 4 plus 16 with respect to x, which is going to be, we raise the first power to 9 and divide by 9, so we have 9x to the 9 divided by 9 plus 24x to the power 5 divided by 5 plus 16x to the power of 1 divided by 1 plus our constant of integration c. I'm going to just tidy up my coefficients, or that first one at least, so I just get x to the 9 plus 24 over 5 x to the power 5 plus 16x plus c. So for the achieve mark, you have to do this correctly. It does say that C is not required, which seems a little bizarre, but there you go. They've been lenient on this paper. So expanding the brackets and integrating each term, fairly straightforward. Achieve for the right answer. C, not important here, but for goodness sake, always write it unless you're given bounds with which to integrate between. Now, for part B. We are told to find the value of k given that the integral between 16 and k of 3 multiplied by the square root of x with respect to x will be equal to 112. We must use calculus, So we're just going to integrate it with respect to x and set it equal to 112. Easy as that. So integral of 16 between 16 and k of 3. I'm just going to rewrite the square root of x as x to the power of half with respect to x is going to be equal to 112. So then, slapping it straight in my square brackets, I'm going to have my 3x, the power is raised by 1, which is the same as 2 halves. 2 halves plus 1 half is 3 halves, divided by 3 over 2 between 16 and k, and that's going to be equal to 112. Now 3 divided by 1.5 is equal to 2. So just to make my life a bit easier, I'm going to have 2x to the power of 3 over 2 between 16 and k is equal to 112 again. So now I get to substitute all this into a calculator. 2, big bracket, sorry, 2 multiplied by 16 to the power of 3 halves minus 2, oops, not 2 there, sorry, k to the power of 3 over 2 is equal to 112. Now we're just going to work out what 16 to the power of 1.5 is, multiplied by 2. It gives me a 120, oops, sorry, not on the page, 128 multiplied by, minus 2 multiplied by k to the power of 3 over 2 is equal to 112. Now I'm going to do two things at once here. I'm going to add 2k to the power of 3 over 2 to both sides, and I'm also going to subtract 112 from both sides. So I get the k on its own, or the k term, sorry, on its own. I'm going to do 128, take away 112, leaves me with 16. Therefore, k to the power of 3 over 2 is equal to just 8. Therefore, k is equal to the 8 to the power of 2/3. If you do that, you find that k is equal to 4. Sorry, maybe I should explain why I just did that. If you're trying to undo a power, if you put your power, so I'm going to work in blue to the side, just to explain that, sorry. If you have your k to the power of 3/2, and you want your k to be to the power of 1, the way that you make any fraction equal to 1 is to multiply it by its inverse. So you would multiply 3/2 by 2/3. Doing that would give you 6/6, which is 1. If I've multiplied this power by 2/3 using my power rules, this is the same as having k to the power of 3/2 to the power of 2/3. So I've effectively put this entire left-hand side to the power of 2/3. Therefore, I must also do the same to my right-hand side, putting it to the power of 2/3. If you put that in a calculator, you get 4 because this is effectively the same as 8 to the power of 1/3 squared. Again, separating 2/3 into 2 times 1/3. The cube root of 8 is 2. 2 squared is 4. So that's what that last jump was here. Just using your power rules and your fractions being inverse to get 1. Okay. If you did all of that, you got k equals 4, then that was achieved. It's a lot of work to achieve, but that's what you need to do. And then we are on to part C. We are told to consider the differential equation dy by dx is equal to 12y squared multiplied by e to the power of 3x. Given that y is equal to 0.5 when x is equal to 0, find the value of y when x is equal to 1/3. Now, whenever you have an expression given to you in this form, the key idea here is you want to get all the things pertaining to x on one side, all the things pertaining to y on the other. Where you leave any coefficients, any numerical coefficients or constants, doesn't really matter as long as you remember it's there whenever you're doing the working. So if I have dy by dx is equal to 12y squared e to the power of 3x, I would like my x's to be on one side and all my y's to be on the other. Because I've got e to the power of 3x over here, I'm going to keep my x's where they are. I'm going to multiply both sides by dx, so that the dx goes over onto this right-hand side. I'm going to divide both sides by y squared, so that my y's appear over here. So after those two steps, dividing by y squared and timesing by dx, in reality, these are not terms you can just move around like this, rearrange them. It works, but it's not, doesn't matter. If we do both those rearrangements, we get 1 over y squared dy is equal to 12 e to the power of 3x dx. And to make this an expression or something that we can work with, we just slap our integrands in the front and we can sum over each of these infinitesimally small pieces of y and x. Now I'm just going to rewrite this first one in index form. Y to the power of squared, or 1 over y squared, is just y to the power of minus 2 dy is equal to 12e 3x dx. Then we're going to do both integrations, not with bounds. We have got some coordinates here, but these are the ones where you can find your constant of integration from these coordinates rather than using them as your limits. Because we're doing two integrations at the same time, you can just combine both of the constants of integration together into one overall constant, which is what I will do in a sec. So let's do this integration. If we're integrating y to the power of minus 2, we raise the power by 1, we end up with y to the power of minus 1 divided by minus 1. This is equal to 12e to the power 3x divided by 3. Just dividing by the power of e in its differentiated form, which is just 3 on its own, plus our combined constant of integration. We're just imagining that we had this other constant of integration here, b, because these are both unknown constants, just for simplicity's sake, and to minimize writing, basically, we combine them into one overall constant of integration. It just gives us one constant to find when we're doing our subsequent working. So I'm just going to rewrite this in a slightly nicer form. Minus 1 over y is equal to 4e to the power of 3x plus c. Now we can make use of the coordinates we've been given. When y is equal to 0.5 and x is equal to 0, y is equal to 0.5 when x is equal to 0. Therefore, we can work out our constant of integration. So making those substitutions, y is 0.5, x equals 0, goes to minus 1 over 0.5, which will become minus 2, is equal to 4e to the power of 3 times 0 plus c. Minus 1 divided by 0.5 is equal to minus 2, is equal to 4e to the power of 0 is just 1. Anything to the power of 0 is just 1. Is equal to 4, my gosh, is equal to 4 plus c. Therefore, if I subtract 4 from both sides, I find that c is equal to minus 6. Then I'm going to rewrite my expression fully with my newfound constant of integration. Minus 1 over y is equal to 4e to the power of 3x minus 6. I'm asked in the question to find the value of y when x is equal to a third. So that's what I'm going to do. Minus 1 over y is equal to 4e to the power of 3 times by 1/3, minus 6. I'm going to do that on my calculator now. So e to the power of 3 times a third is e to the power of 1. So I have 4 times e. I've just simplified it down to this. So I have that y is equal to minus 1 over y is equal to 4.873. I'm not going to delete this from my calculator to save having to type it all out again. This is not equal to y. To make this equal to y, I need to times the answer by minus 1, and I also need to put it to the power of minus 1. So having minus answer all to the power of minus 1 gives me minus 0.2052. I don't have any decimal places to give it to. That'll do. Okay, sure. Nice. So we found y when x equals a third. Nice. So let's have a look at the mark scheme quickly. If you found y is equal to minus 0.2052, nice. If you get this, this is enough for merit. Now the mark scheme says any reasonable rounding. So if you did write the full number out, doesn't really matter how many decimal places you round it to, as long as you can see the size of the number. So maybe to a bit more than minus 0.2. Okay. If you got to this, if you had done the integration successfully, so getting to this expression here, or this equation here, minus 1 over y is equal to 4e to the power of 3x plus c. That was enough for achieve. Therefore, if you failed to sort of deal with the y's here and splitting up your respective variables, then you would have been struggling to do the question. So if you are asked to do calculus with combined variables like this, or if you're asked to do integration, you must rearrange the expression, get all the y's on one side, all the x's on the other, then you can sum over all of those infinitesimal sections. Like that. And now we will start having a look at question D. Now D it shows us a graph. It says the graph below shows. That did not make sense. The graph below shows part of the graph of the function y is equal to sine squared x, where sine squared x is this curve, and we have y equals 1, x equals pi over 2, and minus pi over 2 labelled on. This is shaded grey, so we can see almost immediately what we're going to be doing. Find the shaded area enclosed between the lines y equals sine squared x, y equals 1, and our two x coordinates. We must use calculus, yada, yada, yada. Okay, so as we had a similar one before, we are going to find the area under y equals 1, and we are going to subtract the area under the y equals sine squared x, because that would be equal to the white area. Doing the area of the y equals 1 bit minus the area of the sine squared bit will leave us with the area shaded. So area under y equals 1 line minus a under the sine squared. Okay, therefore we are going to integrate our respective lines with respect to x in the bounds pi over 2 and minus pi over 2. Now our expression for y equals 1 is just y equals 1 minus sine squared x. And we are integrating with respect to x like that. Sorry, I did my with respect to x in my sine term. Now, integrating the square of sine is a bit of a job. And as ever, if you are trying to integrate stuff that just seems a little bit unnecessary, remember that we have our trig IDs for a reason. If you look down, we're looking to replace our sine squared term with any normal, just singular power of a trig function. If you go down to your double angle formulae, you have various expressions for cosine of 2a. One of them being 1 minus 2 sine squared x. Sorry, a. Okay. Now this isn't perfect for us because we don't have 1 minus 2 sine squared. Therefore, what we have, if we wanted to make this expression equivalent, we would have to halve everything. So if we have half cos of 2a equals 1/2 minus just 1 sine squared, then we can make a substitution. The fiddly bit comes where we're splitting up, because again, we haven't got a half in our expression, we've only got a 1. So we're going to split the 1, this is the long way of writing it out, into half plus half minus sine squared of x. Now I'm doing this just to illustrate the simplification that's going on. 1 is the same as half plus half, so there's nothing incorrect about what we've written here. But what this means is now half minus sine squared matches this identity. And so we can just change these two terms for half cosine of 2a, which is much more manageable for our calculus work. So half, and we're substituting this whole section for half cosine of 2x, because that's the other change, is we're doubling the angle with respect to x. Now we can just integrate these two as we would normally. So my square brackets, half integrated is half x. In reality, we could have taken a factor of half out the front, not going to, so I can't be bothered. Half x. Then if we're integrating cosine, we get back to sine. So I have half sine of 2x. And because we're integrating now 2x, we have to divide this term by 2, the derivative of the contents of the brackets. And our two limits are pi over 2 minus pi over 2. And now we can substitute these in. I'm just going to rewrite it out without square brackets and with this divide by 2 simplified. So we're going to have half of pi over 2 plus 1/4 sine of 2 pi over 2, or just pi, all minus half of minus pi over 2 plus 1/4 sine of minus 2 pi over 2. Close our brackets. Now again, you can either pump this into a calculator and work out your answer. What I'm going to do is just quickly sketch my sine curve, just to remind myself. 2 pi over 2 cancels down to pi. At pi, sine is equal to 0. So I have half times pi over 2. Half of a half is 1/4, so pi over 4 plus sine of pi is just 0, and 1/4 of 0 is still just 0. Now I have minus pi over 4. Minus a minus. These two negatives combine together to make one big positive. There are much nicer ways of doing that, but joining the two and making them positive is quite satisfying. And again, if you went back to the minus section of the sine curve, sine of minus pi is still equal to 0, so we're still subtracting 0. Pi over 4 plus 0 plus pi over 4 minus 0, there's no bracket, is equal to pi over 2. Now, altogether, that is a merit question. If you rounded your answer and so got rid of the pi, it wasn't in terms of pi, then that was also acceptable. Generally, unless it's a show that, and you're dealing with pi's in your answer, I would always leave the pi unrounded, because I just would. If you got to the stage where you had done the integration successfully, then you would get the achieved mark. So again, use of the identity is assumed, and the resulting integration is what you need to do to achieve. If you get pi over 2 as your final answer, make it nice and clear, then that's merit. And then we're on to part E. Now for part E, we are told that the mass m of a spherical object with radius p can be approximated by the following integral, where a, b, and p are all positive constants. Using this formula, find an expression for the mass of a spherical object, giving your answer in terms of a, b, p, and pi. Now, in the mark scheme, it jumps through quite a lot of steps in the first line. It doesn't really explain what's going on. Some of you will be able to figure out nearly all of it. I'm just going to talk through those individual steps and the justification for it. Now, in this original integral given here, This is one of those patterns that we should always be looking out for. It's written in such a way that makes it quite difficult to spot. If you have an expression containing something to the power of 3 and it's being multiplied, or there is that same variable to the power of 2 in the numerator, so here next to it or on top, then hopefully you can see that the squared term is a differentiated form of the cubic term. And because it's in a fraction, we are dealing with a natural logarithm as our end result. Now, we can't do the integration straight away as easy as that, now we know that. The reason I'm saying that is because we are going to try and simplify the expression in the integrand and take a number of constants out of the integrand to make that natural logarithm integration a bit easier. Now, the easiest thing to do here is to just take 4 pi, because it's already just 2 constants, out of the integrand, put them out the front. So we have that m is equal to 4 pi between p0 r squared a over 1 plus br cubed, all integrated with respect to r. Now, if we were to take out the constant of a, this fraction is a over 1 plus br cubed. Therefore, if we're to take away the factor of a and put it out the front, this will be replaced by 1. 1 over 1 plus br cubed. So we'll do that as our next step. M is equal to 4 pi a between p0, and we have r squared times 1 over 1 plus br cubed. So taking the a out the front, and I've just moved the r squared on top, just because. Now, if we were, because we've recognised that we've got the derivative sort of power on top compared to the bottom, if we just ignore the top of the fraction and pretend we were differentiating the natural log of this 1 plus br cubed, the derivative of 1 with respect to r is just 0. The derivative of br cubed with respect to r, I'm going to work in blue just off to the side so I can show you what I'm doing. If we were to do d by dr of ln 1 plus br cubed, then what we'd end up with is the derivative on top, so 0 plus 2br squared over 1 plus br cubed. Now, the factor of 2 is just a number, so that's unimportant for us right now. What is significant for us here is this b term. Now, we don't have a b on the top of the fraction, and so what's going to happen, or what the mark scheme has done, is to get a b term to appear on the top. They've said that if we multiply all these constants out the front by 1, bear with, write out this crap again, 1 plus br cubed. Now, anything divided by itself is equal to 1. We don't know what b is, but we know if we divide b by b, it will be equal to 1. So immediately, I'm just going to make the substitution. Sorry, this isn't alpha, this is an a. Instead of 1, we're going to have b over b. Now, in truth, the location of these constants doesn't really matter. Due to the nature of calculus, the constants are just passengers wherever you leave them. Sorry, forgot with my respect to dr, with respect to r. I'm going to, and the mark scheme does this in the first step, we're going to move, sorry, I just realised I'm being stupid up here. This is a 3, obviously, you bring down the 3. Don't know why I wrote the 2 there. 3br squared there. Now, if we are to Sorry, we would like to get a sort of fraction that has a b in it. Therefore, we're going to move this top b into the integrand, but leave the divide by b outside, because that's the constant we're not really worrying about. We're just trying to recreate this sort of standard integration pattern for differentiating the ln. So I'm going to drag one of these b's into the integrand, 4 pi a over b between p and 0, br squared 1 plus br cubed. Now we're almost perfect, but we're still missing this numerical coefficient, which is 3 from the cube power that we brought down when we differentiated this contents of the ln. So again, with the same logic that we used to create this b in the numerator, cancelled out by the b with the constants, we can do the same thing with a 3. And it works exactly the same way as introducing another times by 1. So we can add infinite number of fractions to the front of this as long as it's the same, it's a number divided by itself. It doesn't change the value of the expression. We've made this constant very complicated now, but we have made this integration far, far easier, because now it's a direct match for our d by dr. If d by dr of this ln term is equal to 3br squared over 1 plus br cubed, it must mean that our original expression for mass is this natural logarithm expression. So we have that m is equal to 4 pi a over 3b. Then we can finally do the integration, get our square brackets in, natural log of 1 plus br cubed between p and 0. Pardon me, sorry. Then we have the pleasure of substituting all this crap in and processing any algebra, any simplification we might need to do. So we're going to have the natural log of ln 1 plus bp cubed, close those brackets, minus the natural log of 1 plus, where the radius is 0, so bp just becomes 0. Now, what is the natural log of 0? You can justify it to, the natural log of 1. What that's saying is, the power of what makes e go to 1? The power of 0 makes e go to 1. Therefore, this whole thing, natural log of 1 is just 0, and so we have 4 pi a over 3b multiplied by the natural log of 1 plus bp cubed. Sorry, I don't know how long I talked with that off the screen. It's on the screen now. I apologize. Here is what I was talking about, the natural log of 1. The natural log of 1 is just 0. So this whole expression vanishes, and we're left with just natural log of 1 plus bp cubed. Now we have an expression for the mass in terms of a, b, p, pi, and numbers. So happy days. Now, if you did this correctly all the way through, you would get E8. If you made one little error, that would give you E7. And if you got to the stage where you were doing the integration, you had performed the integration, so this step here, that was what you needed for merit. Does not appear to be a way to get achieved in this question, according to the mark scheme. There was a lot of setup to get to that, and it's quite hard to miss, but don't be afraid, like I did here, even if you screw it up, make a fool of yourself, don't be afraid to actually do the reverse operation. If differentiating, if you know that it's going to be a natural log term because you've spotted the pattern of r squared over an r cubed term, then put that whole denominator into a natural log and differentiate it. Then you're just trying to manipulate the constants that may be needed to add it, or the coefficients you may need to add, until you get your differentiated result in your integrand, so you can just do the inverse. Now, the mark scheme doesn't show all that. I would imagine if you just magically ended up with this rearranged expression without doing any sort of step-by-step changes or justifications using differentiation, I would imagine they'd struggle to give you credit. So do show some evidence or some sequence of events that shows you moving various constants around. Altogether, that was question 2. And if you got this expression at the end, that was enough for E8. And now we're on to question 3, the final part of this exam. 3a, find the integral of e to the power 2x plus 3 over e to the power of 4x with respect to x. Nice and straightforward, this one. I'm going to just rewrite it in index form, because that makes the resulting integration far easier, because it's over the e to the power 4x. We just bring it up to the top and put a minus in the power, like so, which then makes this relatively straightforward. E to the power of 2x, we just divide by the derivative of the power, which is just 2. So we have e to the power of 2x over 2, plus, this time, 3e to the power of minus 4x. The derivative of this power is just minus 4 over minus 4, plus our constant of integration c. So yeah, this is equal to half e2x minus 3 over 4 e to the power of minus 4x plus c. That's achieved. You don't need to even write the constant of integration to get achieved in these questions, apparently, which, again, always write it in, never leave it out. You don't need to worry about rewriting it the way I have, like bringing the fractions out to the front. Doesn't look like. So as long as you end up with the expression that has this correct expression, that's achieved. Now, for part B, we are told to solve the differential equation dy by dx is equal to 5 over 4x minus 3, given that y is equal to 10 when x is equal to 1. Now again, these are given to us so we can find the constant of integration c, so it's always important to do that. Now, hopefully we spotted here that we have x to the power of 1 in the denominator and effectively x to the power of 0 in the numerator. What that means is we effectively have the derivative of the denominator in the numerator, which is the pattern for differentiating the natural log of this expression. Therefore, when we integrate it, we will get the natural log of this expression, and we'll sort out any of the coefficients that arise from that. Now, just because we did it literally a few seconds ago, I'm just going to show you how you can justify that again by doing the differentiation of your ln of 4x minus 3. Okay, so we know that if we were to differentiate ln of 4x minus 3, we should have a 4 on top. Currently, we've got a 5 on top. And so we know roughly what our end expression is going to be. But what it helps us to confirm is that we can just divide the top by 4. We know that when we differentiate this 4x, it was multiplying stuff by 4. So when we're integrating, we can just divide by 4. So if we integrate, we haven't got any bounds, 5 over 4x minus 3 with respect to x. Sorry, I'm going to drink water. Is equal to the ln of 4x minus 3 still multiplied by 5, but divided by that 4, plus c. Plus our constant of integration c. Now, we get to substitute our two values in here, because now we have that this is equal to y, therefore 10 is equal to 5/4 of the natural log of 4 times x, which is 1, so just 4, minus 3 plus c, sorry. There was something missing. Now, if you do 4 minus 3, you get 1. The natural log of 1 just goes to 0. Therefore, 10 is equal to 5/4 multiplied by the natural log of 1, which is 0. So 5/4 times 0 is equal to 0 plus c. Therefore, c is equal to 10. Therefore, y is equal, to 5/4 ln, 4x minus 3 plus 10. If you do all that, that's the achieved answer. You had to work out C to get an achieved mark. So that's important. And again, if you are spotting these fraction these natural log integrations, it is a really good idea just to make sure you're in the right ballpark, that you do d by dr or d by dx of, I don't know why I did that by dr, stupid, d by dx of natural log of 4x minus 3. Okay. So now we're on to part C, and this is quite a fiddly style of question I have seen a few times now. Unlike the last few parts where we've had fractions with the derivative power in the numerator and the original power in the denominator, here we have equal numbers of them. Because of the way this fraction is set up, it's not really beneficial or easy for us to split up this fraction into 2 and simplify it from there. It still leaves us with an awkward term. The way that we split these fractions up is we want to do it in such a way that this numerator, or at least the numerator involving the x term, is in a form that can cancel out with the denominator. Now, for this, we're just going to look at the values of x. We can see that the numerator, the values of x, are twice as large as those in the denominator. Therefore, ideally, we'll do it in blue because it's ideal, doesn't make any sense, but ideally we'd have 4x plus 6 over 2x plus 3, because that can simplify to 2 over 1. Because this is directly double to the denominator. This is almost the same, but it's a 5, not a 6. Now, the way that I've seen people do this, it's either to add and take away a little bit, or you can sort of group stuff together and then add a little correction term. I'll do both in blue side by side, so you can choose the best way, because some people's brains works different ways. So, the way that my mind, whether rightly or wrongly, sees this is something along the lines of, I have 4x plus 5 divided by 2x plus 3. Now, I want this to be a 6. If I add 1 to the top, then this combines to make plus 6. Because I've now changed the value of what was being integrated, if I put this into the integrand, minus 1, I've changed the value of this integrand, so this is no longer equivalent. Therefore, what I would do is I add a correcting term. Whatever I've added into this fraction, I'm going to take it away, but in its separate fraction. So I'm going to subtract minus 1, remembering that it's still over 2x plus 3. Whatever you add into the numerator here, by default, must be subject to the same denominator. So your correction term must also be subject to the same denominator. So I've added 1 over 2x plus 3 minus 1 over 2x plus 3. So my overall change to the equation, the expression, is 0. I haven't changed it. I've just added a little bit to the main fraction and added a small correcting fraction afterwards, which is relatively straightforward to integrate because now I've got x to the power 1 on the bottom, x to the power 0 on top. So this will be a natural log term when I integrate it. Now, the other way I've heard it explained to guys at school, so I presume it's what you do in your maths classes, is to group together your ideal thing as a fraction. So having, so in your integrand, writing n minus 1, 4x plus 6. I don't know how Mr. Jarby words it, sorry. So I'm going to do my best to emulate him. And I'm sorry if I do a crap job of it. Ask him if you want proper maths help. So he does it like this. He writes down the ideal one here and then just adds the correction afterwards. So going, oh, I've got my 4x plus 6. That wasn't what I started with. So I'm going to subtract 1 from it. Then you can separate out these two fractions. The 4x plus 6 stays as 1. This minus 1 over 2x plus 3 becomes a second fraction. And so you end up with, between m and minus 1, 4x plus 6 over 2x plus 3. I don't think the bracket's important now. Minus 1 over 2x plus 3. And obviously both of these are with respect to x. Now, if you look, these are identical outcomes. This is a slightly different thought process or pattern or order in which you do stuff. As they both end up the same way with the same answer, it doesn't really matter. I get the impression this is what you've seen in maths and maybe more familiar with. This is the same idea. It's just done in a slightly, maybe clunkier way. Now, the whole purpose behind this, either way you cut it, is that you have 4x plus 6 over 2x plus 3 in one term, and then that single 2x plus 3 in the denominator in the second term. So with my integration, now I'm going to go to my black pen because I've stopped fanning around giving you choices. You just get to do this integration. Whoops, minus 1 over 2x plus 3 dx. And it is a minus, good, okay, sure. So, this is now precisely double the denominator. Therefore, that first term can be simplified to just 2. That's the reason we're faffing around at the top of the page. It's to get this fraction so it just becomes 2, or a number, whatever the multiple of the denominator it is. Therefore, when you are doing your integrations, now the integral of 2 with respect to x is just 2x minus our natural log of 2x plus 3. Because the x term is subject to a multiply of 2, we're going to divide this by 2. And then that's between m and minus 1. Now, we have to find the value of m, given that this integral in this range is equal to 2m. So I'm going to make that substitution into there now. So now, sorry, not a substitution, I'm going to write down what it's equal to from the initial information. Now I'm going to sub in m and minus 1. So 2m is equal to, the first term is going to be 2m minus half the natural log of 2m plus 3, close my brackets, minus, 2 times minus 1 is minus 2. Just be careful, just in case I forget as well. We've got minus times a minus, so this will become a positive term. Minus, which again will be a positive term when we expand out the brackets. Half of the natural log of minus 2 plus 3. And again, handily, the examiners have given us a natural log of 1, which goes to 0. So just simplifying some of this stuff, minus half the natural log of 2m plus 3 minus 2 minus 2 becomes a big plus. And then because this is also minus, we have a plus half the natural log of minus 2 plus 3, natural log of 1, which is equal, again, you can justify this to yourself with your calculator, is equal to 0. So, because this is equal to 0, I'm just going to cross it out now, just so I don't have to write it out again. And just explain why I've done that there. Now you might notice that I have 2m on both sides. I'm going to subtract 2m from both sides. Therefore, 0 is equal to 0 minus half ln 2m plus 3 plus 2 plus 0. I'm now going to try and speedily do the relevant rearrangement. We are trying to get m on its own. So I'm going to have m down here, ready, waiting for my answer. You don't need to do this. If you're likely to forget what value you're trying to calculate, maybe it's a good idea. You can make your own little answer box at the start of a question. I sort of tell my physics students to do the same thing. Just to remind you, that's what the question wants. It doesn't want just the integrated equation. It wants you to work out m. So you lose the upper marks if you do that. If you don't do that. So I'm going to add half ln of 2m plus 3 to both sides. So I'm going to go quick here because I think this rearrangement will be something that you can follow along with. Oops. And then pump that into your calculator. E to the power of 4 minus 3. Be really careful that you move your cursor out of the power of 4. Otherwise, it'll give you e to the power of what? 1. Sorry, pardon me, which is a very different answer. And so you should get 25.79907 blah, 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 is equal to, the mark scheme was given them all to 4 sig fig, so 80. Okay. Now, if you're not careful when you're typing this into a calculator, I'll just demonstrate the point. If you've just put in your e to the power 4 and do minus 3 here, you get 1.359. You have to move the cursor out of the power. Sorry if it sounds patronizing, condescending. I've seen enough people do it over the years that I want to point it out there. If you get this, this is your merit. No excellence for this. To get achieve, you had to get to the stage once again where you had successfully integrated your expression up here. So seemingly the achieved isn't that much work. There's a lot of rearrangement down to get to your value of m at the end. But just be careful that you do actually answer the question that's being asked, not your own interpretation of what the question might want. If writing your own answer box helps you do that, screw it, do it. And on to part D. Now this question is quite cool, I think. We are told that the graph below shows the function y is equal to 2 cosine of x over 2. This shows here. We are also shown that it is split into area A and B. And on our x-axis here, we have the origin, we have k, and we have pi. Now because this is 2 cosine, the y value is 2, we are told to find the value of k so that the shaded area A will be equal to the shaded area B. So we want A of A is equal to A of B. That is what we are demanding. Now, the area of those respective areas is the area under the curve, and it is under the same curve, but we have different bounds. So the area of A is the area from 0 to k, which must be equal the area of k to pi. This isn't mathematical notation particularly, this is just helping to justify why I'm about to do what I'm going to do. Now, to find the area from the curve, we are going to use integration. It's going to be the same integration that we do to the cosine term. However, the way we define the integral, the bounds of the integral will be different for each one. So for area A on the left, we're going to integrate between k and 0, our 2 cosine x over 2 with respect to x, and we are setting that equal to the same integration between pi and k. 2 cosine x over 2 with respect to x. Okay, so now we're just going to do it. If we integrate cosine, we go back to sine, so we're going to end up with 2 sine x over 2. Because the x term is subject to a factor of a half, we have to divide by a half. Dividing by a half is the same as timesing by 2. So I'm just going to add a times 2 here. Actually, no, I'm not, because that's not very rigorous. I'm dividing by a half, which is the same as timesing by 2. And that's in the range k to 0, which must be equal to the exact same integral x over 2, again divided by a half. Pi, not 0, pi and k. Now, hopefully, you can start to see where this is going, as we are going to have the sine of, we'll get there when we get there. We've got pi's and zeros involved, so we know there's going to be some ones and some zeros that get cancelled. I'm going to sub everything in, because that will just make it really easier to explain what I was about to say. 2 sine, if we're dividing by a half, we're timesing it by 2, so I'm just going to change it to a 4 now. 4 sine of k over 2 minus 4 sine of 0 over 2. That is all equal to, again, 4 sine of, this time, pi over 2 minus 4 sine of k over 2 again. So now, I'm just going to, if we remember our sine curve, at 0, sine is 0, at pi, sine is 0, at 2 pi is 0. Therefore, at pi over 2, it's equal to 1. Because we've got 4 lots of it, it's actually going to be equal to 4 on this curve. In much the same way that here there was a 2, so the max value was a 2. Now, because it's a 4 multiplied, the max value is 4. And then we're going to go through and hopefully tidy up this expression. So 4 sine, oh sorry, I should say, what did I say? We're going to tidy up this expression. Because every single thing is times by 4, I can divide absolutely everything by 4. So we're going to have sine k over 2 minus sine of 0 is 0. That must be equal to 4 sine of pi over 2. Pi over 2 is equal to 1. 4 lots of 1 and 4. 4 minus sine k over 2. And because I'm silly, I forgot I divided everything by 4, so this is going to be 1, sorry. Therefore, I can bring this sine term over onto the other side. If I add sine k over 2 to both sides, I get 2 sine k over 2 is equal to 1. Now, don't panic and go looking for any trig IDs. Because it's just equal to 1, I can divide by 2. So sine of k over 2 is equal to a half. Therefore, k over 2 is equal to sine minus 1 of 0.5, which gives me pi over 6 radians. Therefore, k is equal to pi over 3. Okay. If you did all that, that was merit. If you integrated your two cosine terms into the sine terms here, this step going from here to here, that was enough for achieved. There was an alternative method mentioned in the mark scheme. Hang on, I'm going to look at what it was. The whole area is equal to that. Okay, so what they do is instead of doing the individual limits and doing two integrations, you do one integration over the whole area. You find the total area, which if you did this, you would find it would be 4. Therefore, each individual area would be 2. And so you can integrate, let's say, this first area with respect to x between k and 0, knowing that the area must equal 2. So if you integrate over pi to 0 for this expression, you'll find that the area is 4. Therefore, the area of one of these halves, if they're both going to be equal, would have to be 2. Then you can integrate this over its little range k to 0 and set it equal to 2 to find the value of k. Either way, k is 1/3 pi. And then we're on to the last part, part E. Oh my god, this is a wordy one. Okay. Sorry, I ran out of space on my computer. So I don't know where this got up to. I'm not going to read this all out. I just can't be bothered. The important bit that I'm going to highlight, however, is that the rate at which the temperature of a cup of coffee changes at any instant is proportional to the difference between the temperature of the coffee, N, and the temperature of the room. So the rate at which the temperature changes is going to be dN by dt. And this statement tells us that it is proportional to the difference between the temperature of the coffee and the temperature of the room. The temperature of the room was 18 degrees. So this is proportional to N minus 18. Now, if we don't know what the constant of proportionality is, we can just enter our own unknown variable. There's not really a right letter to use for this, but often we use K for undefined constants. I don't really know why, but there you go. So you end up with a differential expression somewhat like this. Now, we want we want to solve this to find the temperature of the cup of coffee when it was made. So we need an expression for temperature. Sorry about that. So we need an expression in for the temperature of the coffee. Now we have another case where we have n variables split up and we want to fix that. So we are going to just move our dt over to the other side and we're going to divide both sides by n minus 18. That'll bring our n term over here and leave our dt over on the right. So if we do that, we get 1 over n minus 18 dn is equal to k dt. Now, as this isn't really a real expression you can write just like this, we need to add our sums over each of these infinitesimal sections of n and t respectively, like so. Now we can integrate both sides. Because we're not integrating between bounds and we're integrating twice, we will, in practice, get two different constants of integration, but we can just combine them together as one overall constant of integration. So, if we're integrating this, we have n to the first power underneath n to the 0th power, or there is no n on top. So again, this follows the pattern of a differentiated natural log expression. So integrating it, we get a natural log back. The natural log of n minus 18. I'm not going to write the constant of integration here, I'm going to write it on the other side. Because the n term has no coefficient, we do not need to divide by anything, it's just the natural log of n minus 18. This is going to be equal to k times t, raising t to the first power, plus our constant. Okay? Now, we are told in the information, the bit that I declined to read, that after 30 minutes, the temperature of the cup of coffee is 50 degrees. Now, assuming we're going to be working in minutes, I don't see any reason why we wouldn't. For simplicity's sake, we're going to work in minutes. If you did change it to seconds, you're going to get different constants, but it shouldn't impact things as long as you're uniform with what you're doing. I'm going to use minutes just because it seems to be a bit quicker to do it that way. So the temperature after 30 minutes was 50. So after t equals 30 mins, n is equal to 50 degrees Celsius. So then we find we just substitute those values in. The natural log of 50 minus 18 is equal to, can't see what I'm doing. After t was 30 minutes, n is equal to 50 degrees. The natural log, just substituting those numbers in, is equal to k times t, just 30, forgot where I wrote it, 30k plus c. Now, apologies, I haven't been able to finish this off for a while, so I'm finishing this off on refill. So, we have, I think the computer got up to, where did we get to? Then 50 minus 18 is equal to 30. K plus C. Okay, cool. Nice. So I'm reading the test paper off my laptop this time, sorry. So for the second piece of information you are told in the question, it's the sentence where, the third sentence where it says, the fourth sentence. When the teacher returns again, after a further 1 hour, the cup of coffee has cooled down to a temperature of 30 degrees. Now, the first time we had here was after 30 minutes. A further hour later means that t isn't just 60, t is 60 plus the original 30. So we have the original plus those 30 minutes, the 30 minutes plus the further hour gives us a total of 90 minutes. At 90 minutes, the temperature was 30 degrees Celsius. Okay, So just like before, we can substitute these values into our expression here, and the expression here, and we'll have two equations, both with two unknowns in. In this expression here, there are 4 variables that we're not sure of, too many to deal with. With these pairs of coordinates, we're able to get into some simultaneous equation work. So we'll have the ln of, this time 30 take away 18, so that will be 12, is equal to 90k plus c. Now I'm just going to simplify the 2 natural log terms, and I'm going to write them side by side. 50 take away 18 is 32, 30k plus c. Then we also have the natural log of 30 minus 18, which is the natural log of 12, being equal to 90k plus c. Now there's a number of ways you can go about rearranging these, solving the simultaneous equations. Because you've already got this equal numbers of c and they're both being added to each equation, I think subtraction is the fastest. You could alternatively do substitution, rearranging one of these equations to eliminate either k and c or k or c, and then subbing that resulting answer back in to find the other one. I'm going to do subtraction, but I'm going to do it where this is my second equation, this is my first one. I'm going to do 2 minus 1. So I'm going to do the second one, take away the first one, just because I've got more k's. So, yeah, personal preference. My natural log of 12, therefore, is being minus 32, and that is equal to 90k plus c minus 30k minus c. Sorry, off the edge. Because what we're trying to work out in this question, solve it to calculate the temperature of a cup of coffee when it was made. Okay, when T is 0. Cool. So now what we can do is gather up like terms and cancel out those that we need to. I'm going to leave the natural logs because there's not much benefit in condensing them down any further. 90k minus 30k is equal to 60k. C take away c is 0. So we're just left with this. Therefore, k is equal to the natural log of 12 minus the natural log of 32, all divided by 60. And then you'll throw that into a calculator. Ln 12 minus ln 32 over 60. Syntax error, because I missed a bracket. If you ever get a syntax error, it's because you missed a bracket. Maths error is like your square root of negatives, or sign bigger than 1, or something like that. Minus 0.016347, so k, our constant of proportionality, is minus 0.016347. Now that we know that, we can substitute in for we're just going to work out what c is now. So we know we can substitute this back into either equation just because it's number 1. K into equation 1. I don't know how you learnt simultaneous equations. I think I got taught with these little 1s and 2 labels. It just helps to explain what you're doing. Sub k into equation 1. I have the ln of 32 is equal to 30 lots of minus 0.016347. Always use your unrounded number. I've left mine in my calculator to save having to type it out. I suggest you always do the same until you finish a question. Plus c. Therefore, c is equal to the ln of 32 plus 30 times 0.016. And I can type it into a calculator. Ln 32 plus 30 times my answer. Sorry, I put a minus in there just because my answer is saved as a negative. and I should find that my C is equal to 3.95615 C. Okay. Now, because my expression is in terms is equal to n, where n is the temperature. Oh, I just know what, we're not going to faff around with that. We're just going to move on because it hasn't worried about units all at any point in this question. So I'm just going to forget it. Now, the actual question was asking for the temperature of a cup of coffee when it was made. First of all, I'm just going to write out our expression in full now. So ln of n minus 18 is equal. So whenever you've worked out all these various constants in an equation, it's a good idea to write the equation out in full, just always, because it's often a marking point somewhere along the lines, equals k times t, which is minus 0.016347 multiplied by t plus C 3.95615 ... So to find the temperature of my cup of coffee when it was made, that is when T is 0. Find N at T equals 0. And so that's what we shall do. Now we want to get N on its own, so I'm going to put everything to the power of E. So, N, everything to the power of E means that the natural log just becomes N minus 18 equals, then E, this, everything goes in there, E to the power of, just to save a bit of time and my brain, because T is 0, this entire term becomes 0. So 0 for the first part plus 3.95615 . Now, I want to find N on its own, so I'm going to add 18 to both sides. 18 is not in the exponent. Because I've kept my answer in my calculator waiting, I can just press alpha E to the power of answer plus 18. Whoops, sorry, it's really hard for the sun to show you what I'm doing. Gives you an answer of 70.2557. This is in degrees Celsius. I'm going to round it to 4 sig fig because that's what paper's been doing, as I recall. 2 6. Where's the mark scheme? Give me 1 sec. Okay, so if you got N is equal to 70.26 degrees Celsius, that is 8. It says any reasonable rounding here, so as long as you're sensible, that doesn't matter. As ever, make sure you use the unrounded numbers wherever possible because this is very close to being rounded down or differently anyway. So always use the unrounded answers. Hopefully, if you keep them saved in your calculator, you won't have to retype any of them out. Like here, handily, T was 0, so I didn't need to write this out in full. Maybe get lucky, maybe you have to go back and recalculate the number, but hey ho. If you just got to the very first, sorry, I rewrote my first steps at the top. If you got to this bit here, did the integration successfully to both sides, then that was enough for achieve. If you found K and C without doing integration, then you could only get merit. And if you had used hours or seconds, you would have got a different constant of proportionality, K, I believe your integration constant would have been the same. So yeah, if you did convert your units for time to seconds or hours, it was still possible to get full credit, but naturally it would have changed the numerical answers. If you worked in minutes and you've got 70.26 degrees, that was E8. For E7, sorry, laptop's under here, there was one error allowed for E7. Altogether, that was question 3. That was the last part, I think.